Welcome. So we had done this problem. We talked about it in class, but I wanted to go over it again just to make sure a few things were clear. Right? Hopefully how to set up your conditional probability tree here is clear. Right? So, and I'm going to kind of review those steps one more time in general. So notice we have each of our categories. Right? And we have the probabilities for those first categories, which is the 0 siblings, 1 sibling, 2 or more. And then each of those categories is broken up into the next set of categories, which is own and share. Okay? A couple things I wanted to point out is that each branch set has a total probability of 1. In other words, when we look down the first branch set, which is the 0, 1, 2 or more, notice 0.2, 0.6, 0.2 adds up to 1. When we look off of each branch set off of each of those probabilities, they add up to 1. 0.9 plus 0.1, 0.8 plus 0.2, 0.5 plus 0.5. And now let's see what happens when we multiply to get our probability of both events. We have to multiply across the branch. Right? Because we're looking at the probability of two things occurring, and we multiply to get those probabilities. Right? So 0.2 times 0.9 is going to give us 0.18. 0.2 times 0.1 is going to give us 0.02. 0.6 times 0.8 is going to give us 0.48, excuse me. Yeah, that would be an impossibility. 0.48. 0.6 times 0.2 is 0.12. 0.2 times 0.5 is 0.1. And 0.2 times 0.5, of course, again, is 0.1. When we add these probabilities, 0.9 plus 0.02, that gives us 0.2. 0.2 plus 0.48 gives us 0.68. 0.68 plus 0.12 gives us 0.8. 0.8 plus 0.9 is, 0.8 plus 0.1 is 0.9. And 0.9 plus 0.1 is 1. Those add up to 1, and that's no coincidence. It has to be that way. Right? You have to have all of your outcomes represented at each branch level. Right? So there were 3 outcomes for the sibling, and then there were 2 outcomes for each of the room situations. Right? And so the siblings adds up to 1. It's not something we forgot to add, put in there. We didn't leave off something. And then everybody can fit into one of those categories. Right? You either have 0 siblings, 1 sibling, or 2 or more. Right? That covers everything. Right? And then the 2 options where you have your own room or you share a room. There isn't anything else. Right? And notice that each of those has to add up to 1. Has to give us all of our outcomes. And then when we get our conditional probabilities and we add them up, those have to all add up to 1. Okay? So these are conditional probabilities, but when we calculate these, because they've already been broken down for us to easily calculate out any category, we're going to use that fact. And so if we want to find the probability across the branch, right, we're going to follow the branch and multiply each of the probabilities. Right, so the first one, I just want to kind of go through that again, make sure it was clear. So that first one, what that means is the probability you have your own room given 0 siblings. So that means I need to go down the branch with 0 siblings. I'm not going to go down any other branch because it's given, that given tells us where to start. Okay, so we have to start down the branch with 0 siblings. So your own room, given that you have 0 siblings, we just follow and multiply the 0.2 times the 0.9, which we have already done because we found all of them. So that's 0.18. Right? So that given is going to tell you which branch to go down anytime you're dealing with a probability tree. Looks like my G is missing here. So the probability you share a room, given you have 1 sibling, means I need to go down the branch with the 1 sibling, right? So that means I'm going to multiply the 0.16, and then I need to go down, continue down the branch or across the branch. I guess it's better to say across. across the branch that has own room. Right? So I have to multiply 0.6 times 0.8, so that would be 0.48. That's that probability there, right? So you go down, you go across the branch, and the given tells you where to start, right? Which of the two options to start at, and then the first part, the own room, tells you the second part of the branch to go down. Okay? So we want to know the probability you have your own room. So now we have several conditional probabilities to add up. We have to find the probability of your own room given 0 siblings, and we have to add that to the probability of own room given 1 sibling, and add that to the probability of own room given 2 or more siblings. Now we've got all of our probabilities calculated out on the side there, so it's pretty easy now because all we have to do is add up the right probabilities. So own room given 0 siblings, right? That's the 0.18, the same thing we have in that first question. The probability of own room given 1 sibling, right? So then we go down. Oh, I just realized I made an error. I just misread this one over here. So let me step back a second. That doesn't say own room, it says share a room. I put the wrong one up there. So it should be given 1 sibling, you share a room. You need to go down the other branch. You need to go down the share branch. That's 0.12. I think I must have been looking at the own room that's right above it and saw own instead of share. Just needed to fix that. Okay, so now the probability of own room given 1 sibling, that would be 0.48 because we'd go down the branch that says that has for 1 sibling, and then continue across the branch that's for the own room. And we multiply those two probabilities together, which we've already done, which is 0.48. And then finally, we go across the last branch, the 2 or more, and then we head down the own room, although it's the same thing for either one of them because it was 50-50. So it's going to be 0.1. We add that together. And so we add all 3 probabilities here, right? Because it's the probability of your own room given any of the 3 sibling options here. All right, so we just add those together, and that's going to be 0.76. So now if we wanted to know the probability of share a room, well, that has to be, we don't even have to calculate out the whole thing, right? We don't have to add up the 3 probabilities now because there's only 2 options for the room. Either you have your own room or you share a room. Together, those have to add to 1. And so if the probability of own room is 0.76, if we subtract that from 1, we get the probability for share a room. And notice that if you added the 3 options for share a room, the 0.02, the 0.12, and the 0.1, you would get 0.24. So that's just another way to see that one, to check yourself. Okay? So hopefully the factor trees are clear. If not, I can have more examples and go over those in class. And now we're should be moving to a table. Oh no, I want to go over some steps. I want you to put these in your notes. Right? So this was the rules for drawing factor trees. And I kind of very quickly in first period went over those. I underlined the key things. Right? And so I'm going to go over it again. And you should put this in your notes. Hint, hint. Put those in your notes. All right, so the branches that, if you don't like the word emanating, I don't even know. Emanating. The branches emanating. All right, if you don't like that word, you can substitute that come from each point, all right? It doesn't matter, all right? Emanating just means, I kind of had to like read the word. I'm not used to seeing it in print, I guess. Emanating just means that starting from each point. So the branches that start from each point must represent all the possible outcomes in the next stage of classification. So in other words, all of our sibling choices had to represent the outcomes, own or share. Each one of them had to have the outcomes for the next stage. Right? So you can shorten that maybe. Branches must represent all possible outcomes for next stage. Right? You can just shorten that a little bit. Second, sum of all the probabilities on any branch, not even this branch, but any branch adds to 1. So you can even make that on, so you can just put sum of probabilities on bunch of branches adds to 1. You can shorten that a little bit. Just make sure it's still clear with the meaning. And then you label your paths with appropriate conditional probabilities. For calculation, each path corresponds to some outcome. The probabilities of the outcome is the product of the probabilities. You can probably leave off the word along the path. Although maybe that makes it clear that you have to go across the entire branch. And then to calculate the probability of an event, you calculate the probabilities of each path, and then you add those probabilities of the paths. So like the last problem, we had to add the probabilities for 0 and own, 1 and own, 2 or more and own, right? So put those in your notes. You can use these words or put them in your own words if you'd like. But that way you've got all the steps for the tree diagrams. And the nice thing is I don't have to wait for you. You can just pause the tape. Okay, so I'm going to go on. Or you can even look at the lesson once it's posted. But I'd probably just do it right now. Just pause the tape, write it down, and you're good. Then you don't have to look for the page. All right, so now here's the table, and we're going to calculate out 4 problems, right? Including a conditional one, right? So I think we had a conditional probability. We had some conditional probabilities on the last set of tables. I added one here, and I am going to use the conditional probability formula for that one because I think it was much clearer for you when I did. All right, so now the first 2 are really easy, because they are just simple probabilities. There's one thing. So it's the probability you're over 25. Right? So that's just going to be the number of people that are 25. So the over 25 over total people. This is simple probability, nothing compound about this one. So there were 30 people that were over 25. There are 60 total people. So half the people were over 25. Makes sense because there were 30 under 25, right? Half and half. The probability you were for violence on TV. Okay, so this one, because we have the totals, if we didn't have the totals, we'd have to add probabilities. It's a simple probability, and we don't have to add. I did not leave myself much space, so I'm just going to put a little arrow here. So that would be the total violence, or total for violence, over total people. So again, it's 60 on the denominator there, because that's our total people. And our total for violence was 13. So 13 out of 60, right? And that does not reduce. All right, so now probability. So those 2 were just simple probabilities. The probability probability you're over 25 and for violence. All right. So now we're looking at the intersection, right? So that's the probability 25 and for violence. Actually, no, I'm sorry. I try to color code these so that I can circle them, and then you can follow along. And I've already used blue. So probability of 25 over 25. And for violence. Right? So we're still going to have the total people in the denominator, but now we want the intersection between over 25 and for violence. And so if you just follow where over 25 and for violence intersect, right, you get 3. And there were 60 total people. So that does reduce to 1 over 20. All right, so now the last one, this is a conditional probability. And we'll still do more with conditional probability, but I put it on this for the table. So that's going to be the probability. So this was probability you're against violence given that you're under 25. Right? So it's going to be where these two intersect, the probability you're against violence I'll just put against instead of having to write out violence again. And under 25. So it's where those two intersect over the probability of the second. The probability of under 25. And that's going to give us the probability of against violence for the group under 25. Under 25. Right? So now we're going to have two probabilities here. One for the intersection and one for the under 25. All right, so the intersection, now we just follow where against and under intersect. Right? So if I follow against and I follow under 25, I see they intersect right there. Right? So that was 20, and it's going to be out of our total people again. Every single one of these is out of 60 in the denominator. Right? So out of our total people. Right? And then divided by the probability you're under 25. Right? So that's going to be the total 25, which is this one here. Put a little check mark. That's the second one. And so this was the So when we look at our conditional probability formula, right, it's the probability of our I don't want to say it. So the probability, so let's call this B and A, right? So it's the probability of the intersection, the probability of B given A is the probability of that intersection over the probability of that second one, right? Right, so the against and under that's the intersection, and then the probability of under 25 is going to give us that conditional. So the probability of under 25 is the 30. So this number here, I wanted to label them, that's why. So this was the B event, and this is the A event, right? Oh, excuse me, this is not the B event. This is the B and A event, and that's the A event. I just wanted to make sure it was clear how each of these numbers fits into that conditional probability formula. So divided by 30 over 60. Well, we should really reduce. Right, so that's going to be 1/3 divided by 1/2, which is the same as 1/3 times the reciprocal times 2, which means the probability is 2/3. Okay? So what that means, put a little box around that. That means that given that you were under 25, the probability that you were against violence was 2/3. Right? So I was only looking at our under 25 group. And now if you kind of notice, if we just looked at 20 and 30, we would also get that 2/3. Right? So the against violence only for the under 30 group, we still get that same probability. And that's because each of these has been divided into categories. Right? So if you only looked at the right category, you could also get the probability. But you don't have to even do that. You could just use your conditional probability formula, fill in your values, and then simplify. And then you're not wondering, okay, did I choose the right group? Which is the total group and which is the favorable group, right? You just do the intersection over the given. And the given either says given or it has that little line. Both mean the exact same thing. Or is written in such a way that it means the same as given. Okay? So here's this problem. And if you have questions, you can ask me in class. So I'm going to go over at least this, and I do want you to put this in your notes. I would put everything in your notes, then it'll be really, really clear. Right? So on this one, you have a little bit of a page of notes, but quite honestly, I wrote this out. It didn't take me that long. And that is, how do you determine if events are independent or dependent? Well, you use your conditional probability formula, and it's really straightforward. It's really easy to figure it out, so long as you follow the steps. And I have an example. Right? So I have how you tell in the form using the formula. I kind of explained it in words, and then I showed you an example. Right? And everything on this first page has to do with independent. Oh, by the way, you do not have to write the typed part up there. I've kind of explained it. And just write the explained part where it says notes. I think that's clear to follow. So it says 2 events are independent if the occurrence of one event does not affect the probability of the occurrence of the other event. So 2 events, A and B, are independent if the conditional probability equals the probability of the event. And the reason they have it written twice is it doesn't whichever event is A and whichever event is B. It doesn't matter which event you decided to use. Right? Just pick one of them. Right? So, in other words, well, let me go over let me explain that explain that a little bit more clearly, I think, and then let me go over my example, and then I'll come back to why they wrote it twice. All right, so here's my notes, right? And I only wrote it one way to just make any event B. It doesn't really matter, right? So that we don't have to write it twice. So if the probability of B given A is the so the probability of B given A is the conditional probability formula. If that conditional probability formula equals the same thing as the probability of B, in other words, if probability of B from the conditional probability formula, in other words, the probability of B given A is exactly the same as the probability of B calculated on its own, then A and B are independent. Right? So if the conditional probability, if B given A is exactly the same as B, probability of B, then A and B are independent events. Right? So here are the events independent or dependent. Here's my example. So heads and tails. So A is going to be heads and B is going to be tails. The reason they have the formula written twice is I could solve this out twice. I'm going to get the same answer either way. I could say, okay, now B, A, you be tails, and B, you be heads, and so I'll calculate it out again, right? Or I'll calculate it out not for tails now, but for heads, right? Or for heads, not for tails. It doesn't matter, right? You don't have to calculate it out twice. You only have to calculate it once because you'll get the same answer. going to be, if these events are independent, no matter which of the two events you used, you're going to get the exact same thing from the conditional probability formula as you did if you just calculated out the probability. All right, so here we want to know, are getting heads and tails on a coin, are they really independent? Maybe I'm not sure. Right? Maybe I think that getting heads influences whether or not I get tails on the next toss. Well, here with this formula, you absolutely can determine whether or not it's independent or not. All right, so I have to calculate out the combined probability. The combined probability is the product of those two, 1/2 times 1/2, which is 1/4. Okay? So now I'm going to use the conditional probability formula. So the probability of A given B. I could have done probability of B given A. Doesn't make a difference. All right, so it's going to be the conditional probability is going to be the combined probability divided by the probability of the given. Right? And so here I decided that the given was going to be tails. So you can really see it does not matter which one it was. All right, so the combined probability is 1/4. The probability of the given, B here, is 1/2. So dividing by a fraction, same as multiplying by the reciprocal, I've got 1/4 times 2, that's a half. That's the exact same probability as A has. All right? So since the probability of A given B is exactly the same as probability of A, this is since the conditional probability equals the event probability, these are independent events. Right? Absolutely independent events. Now let's look at an example of dependent events. Got this one in your notes? It didn't take that long, right? Did it? And if not, just pause me for a second. All right, so the top's the same. So here, if the conditional probability is not the same, so if the probability of B given A is not the same as the probability of B, then A and B are dependent events. So in other words, if I don't get the same thing when I use the conditional probability formula as I would if I just found the probability of the event, then the events have to be dependent. Right? So A has impacted B. Right? If A has no impact on B, then no matter how I calculate this out, I'm going to get the same probability for B. So A here is green marble, B is blue marble. Are the events independent or dependent? Maybe we're not sure. All right, so there are 10 marbles, 3 are green and 7 are blue. All right, and this is no replacement. All right, so we want the probability of A and B, no replacement. So 3/10 is the probability, so I need the probability of A is 3/10. The probability of B is 7, excuse me, over here. The probability of A and B is going to be 3/10 times 7/9. I don't know why I bothered to write B in here because I really shouldn't have, because he's not the given. So he doesn't need it. What I do need is the combined probability, and I need the probability of whoever I said was given. All right, so 3/10 times, I didn't replace, so 7/9. Right? So, because I took out a marble, right? I took out the green marble, I didn't put it back. I now have 9. I'll draw a picture. So there were 3 green and 7 blue. 1, 2, 3, 4, 5, 6, 7. They'll come in a moment, I assume. All right, so while they're thinking about coming up, I took out there we go. Well, there's most of them. I took out the green marble. I crossed off a green. Hasn't shown up yet, but maybe it will. All right, so I took out a green, so I have 1, there it goes. Oops. But I picked up the red marker before the blue came up. And it made my marbles red. All right, so there I have 7 blue and 3 green. I took out a green, I put it in my pocket. It's no longer there for me to pick. So I only have 9 marbles, and 7 of them are blue. Right? So I could simplify that. That's going to be 7/30. So that's the combined probability. Right? So here we're looking at are the green marble and the blue marble independent events if I do this with no replacement. All right, so 7 over 30 divided by the probability of A. There are 3 green marbles, 3/10. If I don't replace the marble, I've got 7/30 divided by 3/10 is the same as multiplied by 10/3. So there, the probability of getting the blue marble given the, oh, I know why I had it up here. I did need that up here. The actual probability of B. I didn't need it for the conditional probability formula, but I do need it for the last part. All right, so the probability of B given A was 7/9. That's the probability that I would get the blue marble given that I got the green marble on the first pick and did not replace is 7/9. The actual probability of B, which I need for this part, was 7/10. Notice 7/9 does not equal 7/10. Therefore, A and B are dependent when I pick without replacement. So not replacing a marble is definitely now, you can see, a dependent event. We have proved it to be true. Right? And you can prove this with any events. If you have the combined probability and the probability of the given event, you can, and the probability of, if you have the probability of each of the events and as well as the combined probability, you can determine using the conditional probability formula whether or not those are independent events or dependent events, even if you know very little about the two events themselves, right? As long as you know the probabilities. So here, picking without replacing, that is a dependent event. What if I put the marble back? Well, if I put the marble back, I'd have a 7/10 chance of picking the blue marble, and now it's no longer in dependent events, it would be independent. So if I put the marble back, it'd actually be a dependent event because I would have ended up with 7/10. Because I wouldn't have had 7/9, I would have had 7/10. Right? So picking it out without replacement, dependent events, and here's how you prove that. Right? You will definitely have some problems where you have to prove whether or not the events are dependent or independent. I am going to stop here, and then the next set of probably the last podcast is going to have conditional probability again and some Venn diagrams. Maybe the last podcast. So bye for now.